Chuck, I got another idea for an explainer.
Okay.
Now, I've hinted to this probably in different other explainers. I'm going to give it its own topic now. And it's simply, why does ice float? Okay.
I'm going to say because your girlfriend is holding you while she floats on the board. You know she's going to let you go. You know she doesn't love you enough to keep you on that board.
What does that have to do with ice floating?
No, I'm sorry. It's an iceberg reference to Titanic.
Oh, no, we'll get there. We'll get there. All right. So, why does ice float? So, the simple, obvious answer is that it's less dense than water. And anything that's less dense than water will float.
Okay.
Period.
Wait a second. Wait.
Anything.
Just 1 second.
Go.
Anything less dense than water will float.
Yes.
Let's say you have a boat made out of cement or iron or steel, which they do. Steel is definitely more dense than water.
Yes, it is.
So there you go. Suck on that, Mr. Astrophysicist.
Mr. Know-it-all. Okay, it was a major advance in military operations to figure out you can make a boat out of steel rather than out of wood. Because then that would make the side of your boat impervious to cannonballs.
Right.
Or any other kind of sort of traditional weaponry that would take out the wood planks of the side of your boat. When we figured that out, it completely transformed naval forces and naval power. And so it's odd that we didn't figure it out earlier than we did, because the physics was there. But it just you just need genius people to be born and contribute their knowledge.
That's all.
That's all. Okay.
That's all you need.
Okay. So here's the thing: the entire object has to have an average density that's less than water.
Okay.
So the steel boats are not made entirely of steel. You know why? Because they have an empty hull. All right, there's air inside the boat.
Air inside of them.
Okay.
So I see. So the totality of the boat,
yes,
with the hull being mostly hollow,
yes,
full of air,
yes,
the entirety of the structure is now less dense than water.
Yes.
Because when you take it in its totality,
yes,
and you sit it in the water, it won't go down because really it's the air that's kind of
really helping
it up.
And even in aircraft carriers that are fully loaded with missiles and weapons and torpedoes and airplanes that are under deck, still most of that space is air. It's air, right? It's not tight packed airplanes, right? With the wings folded up. There's air all around them. There's air in the offices of the captain and of the ship sailors. So the total average density has to be less than water. And you get that by mixing the steel and the air together.
There you go. Okay.
There you have it.
Well,
and so
it's like, so take that, Mr. Funny Man.
Okay.
All right.
All right. So that's how that works. But by the way, we should be reminded how heavy water is. All right. You don't think about it because a cup of water, you just lift it. But what's the heaviest thing you're going to lug out of a grocery store?
Your gallon of milk or water.
No, there's heavier things than that.
Heavier than that?
And you're going to lug it in the summertime.
I'm going to say fettuccine Alfredo. That might have been frozen. That's very heavy. Always gives me problems after I eat it.
I think the single heaviest thing you're going to haul out of a grocery store is a watermelon. Okay?
Okay, it could be.
Yeah, and they're big.
Yeah. I always do that secretly because I'm black.
Yeah, I know. Yeah, you can't. Nobody can see.
I can't let them see me buying the watermelon.
Somebody's going to get a picture of it. And
exactly.
They're gonna... All right. So, but if you toss a watermelon in a swimming pool, it'll float.
It floats. Yeah. Oh, yeah, you're right. Yeah.
So watermelon is less dense than water.
Okay.
Okay. And by the way, it doesn't bob up like a cork.
No.
It floats low.
Right.
But that just means its density is kind of near that of water, but still less than it.
Yeah.
Okay?
Which would make sense, hence the name watermelon.
Well, yeah, exactly. So another famously heavy thing are tree logs. Okay?
Yeah.
So the Paul Bunyan split, log splitting activity. Well, that tree segment, somebody had to lift that up onto the chopping block. Okay, that sucker is heavy.
Yes, it is.
Okay, it's heavy before you sort of start splitting the wood into quarters for the fireplace.
Yeah. As a matter of fact, it's so heavy. I just had a tree removed from my backyard. And I've never seen a tree cut
Let the
down.
record show, Chuck does not live in the city. Okay, go on.
So I've never seen a tree come down before, like, all from start to finish. Mm-hmm. And so they cut it down in sections, and the last section looks like a giant stump.
Yeah.
Because it is.
Yeah.
And then that portion that they cut off, they let fall. And when it fell, it made a thud that shook my house. I've never seen anything so heavy in my life hit the ground. And they didn't tell me, and it drove a big divot the length of the stump in the ground. I mean, I can't tell you how heavy trees are.
If you were to go there and pick up that toppled stump and chuck it into a lake, it would float.
It would float, yeah. Exactly. I'd also be getting my powers from the yellow sun.
Thank you, Jor-El.
I'm Jor-El's illegitimate cousin. They call me Black Kyle.
That's the one who was living out in the shed, right?
Yes, exactly.
You came to Earth later.
Right. Kyle was messing around.
With the help. Chuck. Stop.
His name was Kyle L. Schwarzenegger.
So my point is, whether something floats has nothing to do with how much it weighs. At all. It has to do with what its density is. I would make that point.
Right.
Okay? All right. And wood is lower density than water, and so all wood floats, basically. Unless it becomes waterlogged, then it might sink. But it floats. And that's why old loggers, before we had cars and trains and things, would log trees near rivers, and then they roll the trees down to the river, and the river would carry the logs down to some port where they would then be milled. And that's how you get a log jam.
Right.
A literal log jam, because the logs would bunch up,
right,
and then someone would have to be there at those nodes and release them, and then all the logs would then continue floating down. Okay, but none of that has anything to do with why I started this explainer.
Which is why ice floats.
It's why ice floats. So what happens is, unlike most things that shrink when they get colder.
Mm-hmm. And believe me, I know that.
Okay. Most things shrink. Why? Because the vibrating molecules take up space. Oh. And as you get colder, the vibrations get more constrained, and so it shrinks.
I'll remember that the next time I step out of a pool.
Okay, a swimming pool.
Listen, it's just vibrating molecules.
That's going to be your excuse.
It's not me. It's the vibrating molecules.
So that's why, if you look at bridges, for example, if you walk across a bridge, there's always places where these sort of teeth joints that can expand and contract, allowing the bridge to not buckle with the temperature changes. Okay, so a lot of construction is conceived and built to accommodate the expansion and contraction from the heating and cooling of objects. Okay, water is the exact opposite of this. Okay, no. So when water gets down to the freezing temperature, so here's what happens. Okay, water does shrink when it gets colder. Now, I only know these temperatures in Celsius because it's a sciencey thing. So we got to go switch over to Celsius. Water freezes at 0 degrees Celsius. So watch what happens. The water does shrink as you cool it by tiny amounts, and it expands as you heat it. By the way, part of the global warming problem is that if you heat the oceans expand. Even if you don't melt ice into the oceans will take up more volume and flood the coastlines simply because the temperature is higher.
Wow.
All right? And if it makes a half of 1% difference in the volume of the water, and you have a 3-mile deep ocean, how much higher is 1/2 of 1% of 3 miles relative to your coastline? Okay?
A lot.
It's a lot. So the water's getting denser and denser and denser and denser. It gets to 4 degrees Celsius, it's at its densest.
Aha.
Okay?
Oh, it's getting crowded.
Get very crowded, okay? And at that temperature, if it's at its densest, that water drops to the bottom of the lake.
Ooh.
Let's talk about a lake now. That water drops to the bottom. Every next generation of water that hits 4 degrees sinks. Sinks.
I see where you're going with this.
Now, okay, so now we're kind of done. We get to 3 degrees, 2 degrees, 1 degree, 0 degrees. We begin to freeze. And frozen water has expanded 10% more than the water that it came from.
Okay.
So that frozen water is floating on top of everything.
Right.
Okay. So here's the most astonishing fact you will learn today, maybe this month, maybe this year. Okay?
All right.
Ice insulates the water below from the dropping temperatures as you enter winter. So, all that 4-degree water that went to the bottom is now shielded from getting any colder
From the layer of ice on the top.
from the layer of ice on the top. So, you build ice, and the ice can get thicker and thicker and thicker, but it'll stay on top. If you're a fish in that lake, if you're a fish, you say, let me just go lower. So in the winter, all the fish stay alive in a frozen lake because they're hanging out at the bottom that doesn't freeze. If water were like every other substance and you froze it at the surface, it's now denser than the water around it, it would sink to the bottom. You would freeze the lake from the bottom up, and all the living creatures and the fishes would be there flapping for oxygen, and then they'd all die.
Wow.
Rapidly. So, the fact that water gets bigger when it freezes protects life in colder climates that survives the winter at the bottom of those lakes.
That is awesome. And I got to tell you, you're right. That's almost as shocking as when I learned that I had a new son.
Okay. All right. So that's up there.
Right. It's pretty up there. And he just showed up like, bing bong, hey, it's me.
So this is a profound fact that is a property of the water molecule.
Yeah.
Water molecules, as we'll call them, special properties. And so now it is possible to completely deep freeze a lake because eventually, if the lake is small enough and the winters are long enough, and if you completely deep freeze a lake, you kill everything. Okay? But the larger lakes do not go through that phase, and they will retain their wildlife for that reason.
That's great.
Yeah. And wait a minute. If ice expands 10%, that means an ice cube, the part of the ice cube that's sitting above the liquid level of your drink, is about 10% of the volume of the ice cube.
That makes sense.
So 90% of your ice cube is below.
And that's why every time you fill an ice cube, the ice tray to its very top, when you come back to it, you have a solid slab of ice that you now have to break, and
Yeah, because it went over the dividers of the ice thing. Right, exactly, because it expanded up to do that.
Expanded up, yeah.
Right. So this is why icebergs, what are icebergs made of?
Ice.
Ice,
or
thank
water.
you. So whatever you see, 90% of it is below the ground, which is what took out the Titanic, basically.
Right. Yeah.
It wasn't the size of the iceberg they saw, it was the size of the ice that was below the water level. And in the original A Night to Remember Titanic movie, they show this huge iceberg that the Titanic collides with. If it was that big, they wouldn't have not seen it.
Right. They saw it from miles away.
Cameron did it right. Okay, James Cameron in the 1996 or 7 version, there was like a little ice cube, a little bitty ice thing there. Okay, they couldn't see it, and they sailed towards it, and they know it's bad, but they didn't see it until it was too late, and it was what was below the ground that ripped out the thing. And so,
and by the way, you're right, because in the movie, the iceberg rips the hull.
yes,
It's not that they collided with it. It's that as they went around it, it grabbed the side of the ship and ripped it open as it went
ripped
by.
it open. So the point is, if you try to make a movie and it's Hollywood and you want people to be afraid of the big bad iceberg, the earlier movie was 1950 something, showed a huge iceberg and saying, "Oh my gosh, we're all going to die." And that's not how icebergs work. And so James Cameron is scientifically literate in many ways and in many dimensions. And if you remember the scene where Jack and Rose, or one of them, they felt that they hit the iceberg. They quickly ran out and looked over, and just this little icebergy thing going by.
Yeah.
Right.
Yeah.
There
So
it was.
look at that. Icebergs are gangster.
Gangster.
Don't see my ones, don't see my guns. They got it all below the surface.
That's how ice rolls, and it's a fun, remarkable thing. And also, of course, this is why you need to leave 10% volume in any liquid food you're freezing in your freezer.
Interesting.
Yeah, if you can't fill it up to the top and put it in the freezer, you'll break the container.
Yes.
Okay, because the water, when it expands, nothing is going to stop it.
Right.
It could be made of steel. It will break. This is how you break pipes, copper pipes in the winter. The water gets in there and it begins to freeze, and bada bing, is the pipe 10% bigger than it was before? No. So it's got to bust a hole in it. Now it can become ice.
Wow, look at that. Yeah. Oh.
All right, so Chuck, let's kick it up a notch, okay? Instead of water 101, let's go water 201, all right? If this is like inside baseball, inside the water molecule. So watch. Let's say you invented some new substance, some new kind of container that is unbreakable, and you put water into that container, filled it to the top, sealed it, and put it in the freezer.
Okay.
Who wins?
Interesting.
Who wins when that water wants to expand? Because everything else, water busts out of your pipes. It'll break your glass. It'll bust your champagne glass, which is very heavy duty. Okay, you try to cool champagne too quickly, put it in the freezer. That sucker freezes. Pop, pop. Okay, so the indestructible container meets the immovable force, or the however that goes.
Irresistible
force meets the indestructible container. Who do you think wins?
I always bet on water.
Okay, here's what'll happen.
Oh wait, how about this? Let me just take a guess. The water will refuse to freeze.
Correct. Okay. Correct. Chuck, I love you, man. I love you, Chuck. Come here, let me give you a kiss and a hug. Okay. So what happens is the container, the indestructible container, will not allow the water to expand, so it stays water.
It stays water.
It stays water.
Wow.
Against the wishes of the molecules. So it stays water, and you can take the temperature down to 0. We're in Celsius land again. 0, 5 below, 10 below. It'll stay water.
Right.
But here's the cool thing.
Why won't you let me be what I want to be? That's why I hate you, Dad. That's why I hate you. You can't accept me for who I am.
What's this with you in the therapy session?
Oh my God.
It wants to be ice, and it's in a container that won't let it.
I'm just trying to be ice. That is who I am. That is who I am. Right down to my molecular makeup, man. And you will not let me be me.
So, watch what happens. So, you pull the container out of the freezer. It's now like at 0 degrees. You now have 0 degree water. Oh my gosh. What is that? Okay. So now you have a magic device, okay, that like either dissolves the casing or unzips it or whatever.
Right.
Okay. In that instant, the entire vessel of water freezes into ice in a fraction of a second.
Look at that.
Because now it has the room to expand, and it does it in that instant.
Wow, look at that.
So in the pipes, in the copper pipes, just to be clear, they didn't break at 32 degrees or 31. A copper pipe is pretty strong, okay? It was holding on to that. And have you ever noticed pipes don't freeze when it hits 32 degrees?
Right.
Or even when it's in the 20s. That's not when pipes break, okay? When do they break? We're down when it's in the teens
right.
in the single digits,
Yep.
where the water finally says, my power to break you, old copper pipe, becomes greater than the strength of the copper pipe itself. So the copper pipe will sustain liquid water down below a freezing temperature. It has some strength to it. That's all I'm saying here.
Yep. It's like, I'm here. I'm ice. I don't care if you are nice. Okay? I'm breaking you.
Oh, is that your attempt at poetry?
I figured I'd go for something. I was just trying to something.
Okay.
I had nothing for the.
You had nothing for it. Okay.
I had nothing for breaking a pipe. Okay. Look, these can't all be gold, people.
That's right. I got you. So there you have it, Chuck. That's ice. I was going to say ice in a nutshell. That broke the nutshell. But no, that's more ice than probably anyone cared to hear.
No, that was fascinating.
This.
That's really good stuff.
Oh, one last thing about floating ice.
Okay.
The less dense it is, the more above the water line it'll float.
That makes
right?
sense.
So cork is like really sitting high up there, and styrofoam barely goes in at all.
Right.
And whereas the watermelon sank very low, and there's like, just a fraction of its diameter there. And so there you have it. And that's how you can make a canoe. The Native Americans would hollow out a wood because they know wood floats, hollow it out, it'll float even better. It floats. Then we learn aluminum, which is a light metal, but it sinks, hollow it out. So now you make a canoe out of metal, right? Because now you put it in the water and you sit in it, you sit down, the total density is less than the density of water. So the canoe floats, you float in it, everybody's fine.
There you go. That's well.
There
I
you
mean,
have it.
I'm not going canoeing anytime soon, but at
Okay,
least
but
I know.
I'll tell you, canoes in their noses, in the tail and the nose, have flotation cushions. Not cushions, but there's like styrofoam in the nose and the tail of the canoe. All right?
Gotcha.
And so you ask, why is that there?
Why is that there?
Can you figure it out?
Well, I guess because it adds, it makes it harder to. It adds buoyancy because it's very
because
light.
if you just left air in there, that would be more buoyant than putting anything in there.
Oh, okay. So then you'd be too light.
No.
Now you got a surfboard.
Now you're flying.
Now you're just right.
No, the reason that's working is because the canoe only floats with the curved side down.
Right. Okay.
If you capsize,
you don't sink your canoe.
okay, exactly, because the canoe's freaking made of aluminum. Okay, so if you capsize it, the middle fills up with water, and the whole thing would just sink to the bottom.
But instead, it floats because it's got the little hollow out.
You got the hollowed out. It's not just hollow. It's got the
right.
with
That's
floaty styrofoam in it.
And basically, it's floaties for your canoe.
It's
It's like arm floaties.
They are floating.
It's like, look.
And if it was airtight, they could just have it a pocket of air, and then they wouldn't need it. But the canoe was just sort of welded in spots. So there you have it, Chuck. Way too much about water. We went way long on this explainer.
Yeah, this was a good one.
Yeah. So
Well, I
good to
gotta
have
go.
you, man.
I gotta go. I'm really thirsty. See ya.
All right. Another StarTalk explainer about stuff you didn't know you should care about, and maybe still don't. Neil deGrasse Tyson here. Keep looking up.